Good, yeah, great. Yeah, great to see some familiar faces, and even better to see some we don't know yet, so welcome all. So over the next 30 minutes or so, I shall try to explain our research project, the Freefall Camera. My name's Tom Shorten. These are my colleagues, David Alatorre, Tom Dryden, and Peter Story. You guys can do your thing. So it's been a long journey for us this morning. We had to travel all the way from the other side of campus. We all actually study here at the University of Nottingham, and we're all studying a master's in mechanical engineering. A large part of our degree is the group design and manufacture project. So over the past 2 years, we've been trying to develop an idea initially sparked by David. So he spoke to a few bigwigs in the department, found us through the skydiving club at the university, and the team and brief were created. So our goal from the onset was to create the world's first autonomous skydiving robot and capable of filming skydivers in action. And we believe this should be done by controlling its position in freefall, controlling its fall rate, and landing safely without any human intervention. No, that one. Cool. So today's presentation will focus on the progress we made last academic year, going through the design process, manufacturing, and then testing of the first prototype, which we have here today. We'll then quickly run through our individual projects this year, and then see what the future holds for the project. You can all breathe a sigh of relief. We've kept out the mathsy stuff and all the technical who do that. Well, no, we've got some of it, so, but not too much. Don't boo me yet.
Wait till the end.
So I'd like to pose a question for you guys to ponder over. Is there a place for robots within skydiving? With us being from the new school of skydivers, we'd like to think so. And this is how we see it. So robots could be used for training purposes, for solo sit and for head down flyers to practice falling down the tube. Just imagine never having to be based again on that free fly jump. We also think it could be used as a tool for camera flyers themselves, to use an external camera, or as a training tool to watch them fly. So it's not very often that camera flyers get to watch themselves for debriefing, say. But all the camera flyers in here, don't worry, we don't think robots have the capability to match your skill yet. So watch out. So yeah, we'll just go through the design process. When we went into the project, we kind of had a good idea of what we were gonna, realistically end up with. Yeah, I know, right? This was my favourite design, and it's a small Android that moves much similar to the way that we do in Freefall. Much to my disappointment, due to the high complexity and cost of this option, meant we had to discard it and move on swiftly. So, see ya. We can have an R, yeah. Another option we considered was to modify a quadricopter platform to suit our purposes, and this would mean eliminating the need for a parachute altogether and thus simplifying the task. This reason was abandoned just due to the fact that to get it to fly at human terminal velocity and also carry its own weight, it would have just had to be too big and too large to be practical. So again, that was onto the scrap heap, and we moved on. This is another one. So basically, very simple, model plane, onboard camera, dives after the formation. Yeah, I know what you're thinking. What can go wrong, right? Yeah, that was discarded faster than the Android one. So we ended up kind of what we had in mind, what David had sketched out 2 years ago. And this was a hemispherical shell with fins and flaps to control its descent. The motors, electronics, and parachute are all contained inside the shell, and it lands using a ram air parachute that can be steered to the landing area. Simple. So after coming up with a few ideas, is this going to play? I don't know. Let's get this playing. There we go. So yeah, after coming up with a few ideas on, yeah, this happens, on what shape we thought best for the robot, we made a few mock-ups, and these were made out of a dog toy and some cardboard aerofoils. That is engineering at its finest. So we then proceeded to lob these out of, yeah, this is engineering. This is what we do, right? So, yeah, so we were lobbing these out of Peter's top floor apartment, and one of us, as you can see from the video, we would be at the bottom ready to catch these with a pillow. I'm pretty sure we only managed to catch one, and I'll take that catch. But we came away with the confidence to, with that shape, and we ploughed on with the hemispherical design. So we made a wind tunnel, a homemade wind tunnel, which David's going to parade for you. Oh, very nice. Basically, because the university only has there you go. The university only has horizontal wind tunnels, and because it was obviously pretty impractical to throw them out of Pete's top floor apartment, we decided to make our own vertical wind tunnel. Watch our Airkix if you're in here. Yeah. So that consists of an electric motor, airplane motor, propeller, and a 12-inch diameter tunnel. So we basically use this to verify the stability of our concepts, to test the control surfaces, and also to keep our housemates and neighbours up at 3 o'clock in the morning. It was about this time that we teamed up with filmmaker Brady Horan and James Hennessy, who run a Nottingham Science Channel. I don't know if you guys have seen many of these videos. A few nodding heads, yeah, cool. Videos began to surface on the internet, and from our initial testing phases, we quickly made a name for ourselves within the department for how little we regarded personal protection equipment. The Dean of Engineering was not so pleased. Called us into his office, and you'll see that in the following videos, after about video 2, I think it is, we are wearing our lab coats and safety specs. So yeah, don't worry guys, we've learned how to do things safely, kind of. So yeah, that's cool. Now this is the CAD model. As I mentioned earlier, we decided on a hemispherical design with aerofoils for horizontal movement, flaps for controlling the fall rate, and its own parachute for getting back down to Earth. So the next challenge was then forming this concept into a feasible manufacturable product. Tom Dryden, who's sitting here at the front, mentioned that he was pretty good with the university's computer-aided design system. It was at this point that all 3 of us chained him to his desk and left him for 2 weeks. Hundreds of hours later, I'm not kidding, he had a CAD model representing our idea, and that was created. So yeah, the next task was then creating all the detailed drawings, parts list, process sheets, and yeah, the list goes on. Another few hundred hours later, and we were finally ready to get our hands dirty in the workshop. Hey. Cool. So yeah, that's some of the drawings that you can see up there. All the technical drawings are using CAD. Lots of hours. So all the parts were made here on the university campus, although almost all the metal components were made from scrap material, and the rest were donations from our awesome technician Jason Young. Between the 4 of us, we managed to fit in the actual manufacturing of the prototype in and around lectures, and so it took us about three or so weeks. We used the university's 3D printing, CNC machining, and water jet facilities to make some of the more demanding parts, and then fabricated the rest ourselves using the student mills and lathes. I love being in a workshop, great fun. So yeah, while I'm talking about some of the other parts, Dave's going to hand out a few parts, I believe. Yeah, so you guys can have a look. Just be careful with them. We've only got 1 of each, and then send them back to the front, like when everyone's finished. That'd be great. This next, yeah, there's me fingering a pistol. It's a bit weird. Yeah. We'll get over that. So yeah, so these are some of the fins, fresh out of the printer, and they were coated with 5 protective layers of paint before we started assembling. This is the mould that, no, this is not the mould, this is the fins. This is the mould that we used to form the top shell, and one of our friends who is, no, he's not here, suggested that this would make a great nacho dip holder. So yeah, each to their own, I guess. This is the robot in the early stages of assembly, and you can just see there, that's the, the bare components. That's what's underneath that orange shell that you've hopefully seen. So over the months leading up to Easter, and this was last year, we finished the assembly, and the final robot is now finished and working, and the grand reveal, here it is. Someone, ta-da! We were going to get smoke and stuff, but a budget,
It's heavier than it looks.
So you're gonna... Yeah, so you can see a photo of it here once Dave's moved out of the way. And this will be at the end, here at the end, so you guys can all come up and have a look, and I think Dave's going to demonstrate it during his bit, which is great. A few statistics, so it weighs around 7 kilograms. pretty heavy at the moment. That's just due to the diameter of the shell. The parachute container is designed for a 30 square foot canopy. The riser attachments, which are these guys here, are solid pieces and they take the brunt of the opening forces. The steering lines go through these and the canopy is then controlled along with a GPS unit. The GoPro camera at the front, as you can all see, we went for the GoPro just because it's the most widely used. There's no sponsorship with them or anything, but we'd like to talk to them at some stage. So that's mounted on a moving bed. So the GoPro is mounted on a moving bed that tilts depending on user preference or changes in fall rate, say. The clever bit is the vision sensor, and that's the one that sits behind the GoPro, and that's the one that follows. At the moment, it's set up to be a glove, which, yeah, there you go. So that vision sensor is linked to that glove, and that basically is how it works, basically, yeah. So it sends that information back to the control surfaces, and that's what moves the robot around. So yeah, clever stuff. And those guys are called Pixie. Check them out. They've got some cool projects out there. A pilot chute, vertical velocity can be controlled by moving drag flaps, and they change the air resistance and therefore the terminal velocity. A pilot chute is stored in this piston here, just at the back. So if you can see that just there, that's where the pilot chute sits, and that's deployed by a spring and an electronically controlled closing pin. Deployment is set to an altitude, and this is read in real time using the onboard barometer. Aerofoils, you can see those, they're used to steer the robot around the horizontal plane, and this is because they have very low drag coefficient, so they're pretty good. All of these features were chosen with ease of manufacturing and reliability in mind, since we knew this would be a one-off, proof of concept. So yeah, that's the robot. We'll come back to that in a bit. Oh right, we added that slide in, did we? There you go, that was a slide. Oh, whatever. Right. We finished our exams like 2 days ago, so this was a bit of a rush. Yeah. Yeah, so I'm guessing most of you want to know how we've been funding this project. Now, up until this stage, we have been working on a tiny budget, and that was the one that was provided by our department for the group design and make project. And that was about 500 quid. So, but due to the expanding complexity of the task, our goals were set, way higher. So we looked into funding from around the university and came across a competition run by the Nottingham Business School. After writing a business plan, which we completely made up, we were, we were shortlisted for the final where we were to present a 5-minute pitch. We ended up coming third, but being beaten by some very worthy competitors, one of which is a friend within the department. But this was fine, by coming in the top 3, we secured decent funding, which meant we could think about real testing from the tunnel and in the sky. This is funny. During the final, we asked Dave to turn up in a suit. I don't think he really got the memo and ended up in his Tatty FS suit. King David, what are you like? Do you know what I mean? This is what I've got to work with, right? So yeah, now we're ready to get serious and begin the real testing phase. We approached a few tunnels and managed to get a phone call with Airkix, and they were intrigued to say the least and liked the sound of our project. So we agreed they agreed to sponsor our tests. Many of you will know John Rogers, the manager of Airkix Manchester, who was incredibly helpful and accommodating to get us in the tunnel to perform our first test. So thanks, John. The tests were carried out to find if the concept worked, which it did. Most of the time was spent fine-tuning the electronic system, but we also found out the range in terminal velocity due to the drag flaps that move in and out. As you can see from the video, which is on the next slide, yes, see if this works. The video is quite stuttery. It's a lot smoother than that. It's a bit annoying, actually. Oh well. This is on YouTube as well, so check this out on the Nottingham Science website. So as you can see from the video, the robot is responding to small movements by the glove, by moving the glove on David's hand. Unfortunately, the Airkix logo has a very similar shade of orange, and as I mentioned earlier, it follows colour, right? So every now and again, it would be like an ADHD child, and just like zoom off onto the Airkix logo. Yeah, we probably should have done a bit of research into that, but we'll make sure we don't make the same mistake twice when we return. It's a shame that's such a janky video because this is pretty cool. Yeah, we'll move on. Cool, so yeah, while looking at getting in the wind tunnel, we were already thinking about how we would get this thing out of a plane. We put some emails out there, and Performance Designs came to the rescue. It was actually in this room this time last year that we accosted John LeBlanc at the end of his seminar and asked him about the possibility of them making us a custom parachute. He was awesome and had some great ideas for us. So about 6 months later, we had an optimum 30 square foot parachute, and this was a huge step in this project. Should we get it out? We get the yeah. Here it is, the tiny parachute. I think that warrants an eye. Yeah, I really do. Should we get it out? Do you want to hold it up, Pete, and then people can see it? Yeah.
F11 or 0P?
It says ZP. No, it's optimum. Sorry, yeah. So yeah, here in this. Yeah, it is. It's tiny, right? Awesome, nice one, guys. Yeah, that's great. Cheers. So yeah, here in this picture, you can see it flying side by side with my old Sabre 150, and PD made it very clear that this was not for jumping purposes. So any of you Software fans out there will be a bit disappointed. So yeah, this thing's tiny, and I still can't believe that Ernesto Gainzer managed to land a 35 square foot canopy in Dubai. That's, it's incredible. We actually did ask him to test jump, but he politely declined. So yeah, instead of doing the first jumps with our prototype here, because that is the only one at the moment, we decided to manufacture a test rig. Basically, that's just a vacuum formed shell which holds the canopy, a few servo motors, and a GPS module, and that's at home actually. Great. So yeah, at the end of the previous academic year, we had built a prototype, had it flying in the wind tunnel, and acquired a parachute. So not bad for a year's work. Since then, we've started our final year. Which means we each have to work on our own individual projects for our masters. But we weren't ready to give up on the dream just yet, so we split the research into 4 sections that relate back to the Freefall camera, and these are as follows. I'm now going to hand over to the guys. They're going to do a couple minutes on each one of their projects. Hello. Yeah, you please. You good? Thanks, Pete.
Thank you, Tom. Okay, hi guys, my name's Peter, and my research this year is focused on the aerodynamics of the freefall camera. So there are 3 groups, what we call groups of control surfaces to the robot. The first is the capsule, which is essentially the body of the robot. Second is the drag flaps, which control fall rate, and finally the aerofoils for horizontal motion. Now my focus this year is just on the capsule, with the aims of reducing the drag coefficient, which will mean that it can be made lighter while still flying at the same terminal velocity. And this will make it safer and easy to handle when on the ground. Okay, so how are we doing this? We could conduct lots of experiments, lots of separate experiments to find the best shape for the robot. This would be terribly time-consuming and expensive. So instead, I'm using a branch of fluid mechanics called CFD, which uses computer software to simulate fluid flow. This software can also suggest changes to reduce drag, for example. So what changes do we expect to see? Well, certainly a reduced diameter, and that will be within the constraints that Tom Dryden will talk about in a second. Possibly a more elongated shape, and hopefully the robot will be lighter. But if we're honest, we don't really know. And if my tutor's research, past research is anything to go by, we could end up with something looking a bit more like this. This started off as a half cylinder, and it's been optimized to have apparently 20% less drag. So yeah, who knows? Hand over to Dave now.
Yep. Whoop whoop.
You're less nervous than
Yes, I'm
Nice one,
David.
Pete, well done.
I'm working on the software, the control software for the Freefall camera, and my colleagues may not agree, but I have the most exciting project of the lot. My focus is going to be on the freefall tracking, which has never been done before, and that's what makes it exciting. My project is split up into 4 separate parts. The first part that I've been working on the whole first semester is to simulate what the robot does in freefall. So this is a picture of the simulation software that I use. Basically, you just tell it what forces it's going to experience, and then the computer basically draws a picture over time of where it's expected to be. And then I'm going to take it to the wind tunnel and do some tests to confirm that it actually behaves the way I expect it to. And once I have a computer model that accurately predicts what it's going to do, I'm going to use that to design the software to control it, to make it smooth, to make it stable. And while I'm designing it, I'm not going to have to be testing in the wind tunnel every other day. I can just simulate it, and I know it's accurate. So that's the, once I've designed the controller, I can take it to the wind tunnel, make sure it actually does work, and then we can test it in the sky and have some fun with it. But I'm also in charge of the programming of the whole robot, so making sure it survives the whole skydive. So that involves making sure it knows that it's in free fall when you exit the plane, making sure that it can follow the skydivers, and if it loses sight of the skydivers, it can enter a searching routine, make sure it can find you again, and it doesn't get too close, it doesn't crash into you, it's all done in a safe manner. So that's another side project, so to speak, that's time consuming. Make sure that it deploys at the correct altitude, make sure that it has an emergency deployment procedure, GPS navigation, make sure it lands where we expect it to land, and a good user interface for setting up how you want it to follow you and where you want it to land. So yeah, easy. And yeah, that's it from me.
Good, Tom.
Hello everyone. Yeah, so I'm Tom. You probably don't recognise me because I have to admit I've only done 3 jumps. But I've learned a hell of a lot about skydiving in the past 2 years from these 3 guys who blabber on about it all the time. But yeah, we've actually found that me not knowing so much has helped a lot in the design process because it points out things that aren't so obvious. So yeah, anyway, as Tom mentioned, I was sort of involved in a lot of the design process and development of the CAD model. So it seemed sensible for me to continue on with that sort of side of things this year. So yeah, this is an exploded view of version 1, which has 78 manufactured parts, these ones that we made ourselves in the workshop. So there's obviously scope there to reduce the number of parts to make it simpler and therefore more reliable. So the main aims of the project would be to reduce costs, improve function by better manufacturing processes than ourselves, using mills and stuff, and therefore improving reliability, which is the end game. We want it to be reliable and safe. So yeah, the project obviously encompasses all different types of research. So the model that I create has to encompass all of that, so I've got to constantly be in communication with everyone to make sure that the model I'm making will fit, say, components from David's research in electronics or the aerodynamic package from Pete. And so, yeah, steering lines and dynamics of canopy and so up to date. I've been contacting local suppliers and manufacturers to get quotes so I can compare different methods and see which is potentially the best for reducing costs. I've been looking into redesign for the drop flaps, which alter the terminal velocity, and what's quite exciting is we're thinking of changing the ballast, which is the majority of the mass, to being variable, so free flyers can also use it, or for people that weigh differently.
You can say it.
Very PC. For thin people.
You get what I mean. So yeah, the models, I'm going to be developing that from now on. So yeah, from now on I'm going to be contacting consultants to try and get some more experienced people involved with the project. Using the money that we won from the grant that Tom was talking about, I'll be using that to produce prototype parts and sort of get the manufacturing stage nearer it would be if we were to sort of sell them, for example. We don't know if that's going to happen. That's mainly what my research is about, to see that at the end of the year I'll make a business model and we'll see whether people want to jump with it like you guys. think that's it. Yeah. Back to Tom.
Cool. Thanks, Tom.
Sorry.
It's all right.
Great. So my individual, cheers, Pete. My individual project this year was looking at the deployment sequence of our parachute, as well as trying to obtain the permission for testing. I plan to use an inertial measurement unit. It's an IMU. Basically, it measures the accelerations and orientation of the robot during the deployment. This graph was taken from John Potvin, who conducted similar tests on using load cells about 15 years ago. So you can see here, this is over a 6 second period. So that's typically, unless you have a Sabre 1, anyone got a Sabre 1? And then it's in about 1 second, right? So you can see where the line snatch occurs, and then you get the brunt of the force occurring here. And that's after the canopy's finished snivelling. So the live drop testing phase is planned out in 4 stages, and we're going to start off with a static line to confirm the parachute flies. First free fall with it deploying autonomously. Then finally the data collection can begin. So some is to adjust the parameters known to change deployment. So we're talking slider size and type, line type, parachute packing techniques, deployment speeds, and just some of them as examples, with the overall aim to decrease these forces to a minimum. So the parachute first flight in the early hours of the morning from a top floor of a secret location on campus, and even at such a low height, it still opened and flew to the ground. Yeah, that's actually Pete's mum's hamper that we attached. All very makeshift here. So we're currently liaising with the CA to gain permission, which is proving difficult to say the least. Bart Gareth from Foxy Planes helping us out. He's on site. And after a very interesting meeting yesterday, the possibility of going abroad could seem like an option. So yeah, to clarify, right now we're ready to test. We want to go. We need the permission, or we need the people to get behind us. Then yeah, we can get that green light and get out there. Yeah. So the next big step for us is, as I said, performing these live drop tests. You know, that's the sort of the last thing that we sort of need to do to qualify it, that it works. We've currently applied for our home drop zone at Langer, which would be ideal as it's only 20 minutes away, you know, but possibly heading abroad. So yeah, in the next 3 or 4 months, I should hope that we've got some footage of it flying, and that's only sort of 1.5 to 2 years since we started working on this project. Tom Dryden, as he mentioned, is working on the design for the second prototype, and the current thought is that the shell will be more bullet-shaped, with the diameter smaller, meaning that we can reduce that weight. We want to change the way the camera tracks itself, tracks the skydiver, moving to an infrared or thermal detection system, as that's likely to be a little bit more reliable. For you free flies out there, we want to design an attachment, as Tom was saying, that can be added on to get it to fall at free fly speeds, yeah. And this is likely to be incorporated onto that next prototype. We also want to be able to manufacture these in using small-scale batch techniques, and this should decrease production costs and increase reliability. Safety, always been our first priority. We want to have a backup deployment method separate from the main electronics unit. Currently it's all together, so we want to separate those two. And thought needs to go into landing patterns and how we can fit those in and around, you know, us fun jumpers. With David being a bit of a whiz with electronics, he wants to upgrade the user interface, perhaps include a touchscreen control panel or a remote that can turn on and off the robot. We have always been, I just want to clarify this, we've always been and still are a research project. We get asked by people, you know, when can they purchase their own freefall camera? You know, we've got no idea. We really don't. So yeah, the future's looking prosperous for sure. Although without the support from the community, so from you guys and regulatory bodies, we've still got just an idea. So you can all help us out by, you know, really getting behind the project, sharing it with your friends, and growing our network of contacts within our sport. Once this reaches critical mass, they're going to have to start taking us seriously. So yeah, just a quick thank you to some people that we've collaborated with this year, and without their support, you know, the project just wouldn't be possible. So yeah, thanks to Radio Skydive UK for our first feature, Skydive the Mag and Liz, Ashley especially, for their continued updates and support, Baz for the cartoon, which we just think is the best, Skydive Lang and Foxy Plane for putting up with our crazy ideas, Airkix for helping us with the wind tunnel testing, the University of Nottingham and UON Sport, who, yeah, just without them we wouldn't be skydiving. Performance Designs for helping us with a parachute, and finally Skydive the Expo and the BPA for hosting us this weekend. So yeah, hopefully this time next year we'll have made a few more contacts, and yeah, if you're interested in working with us, whatever department you might come from, doesn't matter, come talk to us. We're open to all possibilities and ideas, and we'll be around at the end of this talk and, in the bar later. And so yeah, come. So yeah, that's me, done talking, but we want to hear from you guys. So,